Hello everyone, welcome to our channel, and we have a new circuit here. We have this buffer gate using transistor, output LED, resistor, transistor, header, input LED, power on LED, push button. We also have an inverter gate, output LED, transistor, resistors, input LED, header, and a push button. So we're going to make an integrated circuit using a buffer and an inverter. Also, we have here this is an old project I constructed, and these are all buffer gates. We also have the inverter. So let us check the circuit diagram. We're going to make this buffer and an inverter logic diagram. We're going to connect the buffer to the inverter to make this integrated circuit using transistor as a buffer and inverter logic gates. Let us connect. We can connect the buffer to the inverter by using the header. The output to the buffer now is going to connect into the header to the input of the inverter with the use of this header. So let us patch. First, we're going to patch the voltage supply and then the output to the input of the inverter. Let us patch the power supply of the buffer to the pin 1. Now we have the LED power on. Let's connect the output located at the pin number 6 of the header. And then we connect the power supply of the inverter pin 1 to the pin 3 because pin 3 is an alternative power supply pin. And then the power supply connected the negative to the pin number 4. Connected is in the pin number 2. So we have now the power supply for the inverter and the buffer. This is the output. Output of the buffer is connected to the input, which is located at the pin number 8, the input of the inverter. Excuse. Let us connect that. And then we're going to connect the output LED of the inverter located at output of LED inverter pin number 5 and pin number 6. we're going to patch it in here. So let us patch that 5 and 6. This one is the 5 and 6. Should be 4, not 5, 4. So let us check again. Output is in pin number 4, the LED, and then 5, 4 and 5. So we get now here the integrated circuit of the buffer and an inverter. So let us check the truth table. No output. The output LED is turning on. So let us check that. No output at the buffer. Becomes the input. There is a light or input 1. 0, 0, 1. And then we're going to use the switch at the buffer with an input 1. Now we have this input LED 1, and then the output here is 0. We have the input 1 by pushing the switch, the button, and then the final output is 0. 1, 1, 0. So we have now this an integrated circuit using a buffer and an inverter, transistor, logic gates. We can also use it separately as a buffer and inverter. So let us connect again the power supply, positive to the pin 1, and then negative to the pin number 2. We get now the power on indicator for the buffer. Let us check the pin of the buffer 1 and 2. And we're also going to connect the output located at the pin 6. No, pin number 5 and 6, the output LED. And the switch here is here. We're going to use the switch here, just the output LED. 5, 6. So we have now this, a buffer gate using transistor. The buffer, no input, no output. No input, no output LED. This is the input LED, means we have no output. So let us now push the button, making it to 1 and the output 1. Pushing the button, input 1, output 1. So we have now the output 1 or LED turns on. Input 1, output 1. We can also use this inverter gate separately by connecting the voltage supply. Let us connect the power supply, pin 1, pin 2. That is the power supply. We have now the power supply for the inverter. Let us double check. Inverter 1, 2. Also, we're going to connect the output located at 5 and 6. And then we're going to connect the switch located at pin number 6 and 7. The switch. The switch connected to the LED. We're going to connect the LED and the switch. Pin number 6 and number 7. And the output is located at 6, 7, 5 and 6. 5 and 6, the output. 4, 5, 4 and 5, the output. We have now the output and now the switch. 6 and 7. So we have now this, an inverter. Every time you push the switch, LED turns up. Because here, if you have no input with output, no input here, we have the output. And then with the output, this is the inverter 1, putting an output 1, we have an out, putting the input 1, we have the output 0. Putting the output 1, now we have this 0. See, the input LED is turning on, means it's 1, and then the output is 0. That is now how we're going to make an inverter logic gates integrated circuit. We combine the two logic gates to make an integrated circuit or IC. So let us connect again the buffer gate, power supply, pin 1 and 2, and then the output located at the pin numbers 5 and 6. 5 and 6. We have now again the buffer gate, just like this previous old project. So let us make a buffer gate using transistor. We have this diagram, we have the transistor here, and we're going to trace the current flow. 12 volt supply. Upon closing the switch, current flows to this node resistor LED, making this LED to turn on. That's why during the switching on, LED power on is okay. So closing the switch, making the current flows here using KVL, BCC minus the voltage drop, because the resistor diode is equal to 0. Now we have this voltage rating of the LED is 2 volts, so we get 10 volts. Voltage are across RD1. So we need this RD1 to limit the current at LED. To compute for the current using Ohm's law, B is equal to IR. R now is substitution calculation. We get this 500 ohms. 0.02 ampere is the current that flows into the series connection of these two, and that is 0.2, the current rating of the LED to turn on. So we get now 500 ohms. Also the current flows at this R1 to RB1 to B's to emitter junction transistor and to the ground, KVL, making the transistor to conduct in saturation mode because we have now a base regular current. Hertz, where is that? Here. And then by using KVL, we get this transposition, substitution, we get 0.7 volts voltage drop across the transistor in saturation base to emitter. And then we get now the sum of the two voltages, the series combination of the resistor. We get now this BR1 plus BRB1, 11.3 volts. Now we still don't know the value of the resistor here to protect the transistor. Also current flows into the load resistor. I'm picking up the value of the current, or choose the value, the current 0.02 ampere. This is arbitrary values to light this LED, to turn on this LED. That is the required current. So when you push the switch, current flows to the resistor. This is a load resistors. We need that for the load of the transistor, and then transistor goes in saturation mode, almost shorted. So now the current flows here using KVL again. We get this BCC minus the voltage drop RD1, RC1, BCE at saturation equals 0. Using KVL, we have voltage drop here of 0.2 volts that is given in the data sheet of this transistor BC547B. So we get now transposition, substitution, we get voltage drop at RC1 11.8 volts. So there's no current flows here because the switch is open. So we get now this. The value of the RC1 can be computed using Ohm's law. Since we know the voltage drop and then the current that flows, the required current, that is the required current for our design, 0.02, we get now 500 ohms. We are going to compute for the base current here using the transistor formula, because this type of configuration is depends on the transistor formula or the beta current gain of the transistor. Using that formula, current gain, we get IC over IB. We know that IC now, the IC here is equal to collector current at saturation, which is 0.2. That is the current that flows in the shorted path, IC. And then we get this HFE transposition using the formula. We get 200. The HFE of BC547B is 200. So we get now the base current of 0.0001 ampere. That is the current that flows into the base at this state or at this moment. So if we have no input, means the switch is open, we have no output. Current will not flow into the LED because the transistor is in saturation and the current flows into the transistor, making this LED to turn off. So that's why there's no light at the transistor. So let us push the button. Upon pushing the button, current flows into the LED, the power on indicator, and then we're going to push the button, making the LED input LED to turn on, and the current will not flow into the base because it has a very large resistance. Instead, the current flows to the ground, also into the LED, making the LED to turn on. Since this is now cut off, current will not flow here. It is directly shorted to the ground once you push the button. That's why LED turns on. We can compute for the since we already computed the value 500 ohms here, and then we know that is 590 ohms. The collector resistance. Let us compute the resistance here, pushing the switch, resistance to limit the current at the LED same time by using KVL, the same formula. We get 500 ohms. And then using the equation, since we know now the value of R1, 500 ohms, we get now use this equation, previous equation, during this state when the current flows into the base. BR1, BRB1, 11.3 volts. Using that equation and by Ohm's law in terms of IR, since now at this moment current at the R1 and RB1 is equal, making the transistor to conduct in forward bias or in saturation mode. Forward bias of the transistor. Since the current there is in series, equal, substitution, R1, IRB1 is 0.001. Since we know the value of R1, which is 500, and we get now 112.5 kilo ohms RB1. Okay, we have now this 500 ohms, 590, 500, and 112,500 ohms at RB1. So in this state, with the switches closed, transistor operates in cutoff mode, making this an open circuit and the current flows into the LED. That's why every time I push the switch, LED turns on. So let us make this buffer circuit. We have now here the transistor. Upon closing the switch, current flows to the LED. So let us first construct this inverter gate. Okay, let us put the power supply. We have now the power on, and then we connect the output located at 5-6, and then the input switch located at the 6 and 7. 5, 6, 6, 7. So let us connect that. The switch 5, 6. I mean 4 and 5 for the output LED, and then the switch 5 and 6. So it is an inverter. So let us see the circuit diagram for the inverter. We have now here a switch connected, and then I split the two resistor because this resistor we're going to patch this node to the input or the output of the buffer. I'm splitting the two resistor, and we now know that we have a chosen value of R2 590, and we don't know the value RB1, RB2, and then we also have a parallel resistance with the base. Also, we have a load resistor here to limit the current at LED. We have the IC required current for the LED, that is 0.02 ampere. So upon closing the switch, LED turns on. Why? Because this is an LED power on. Computing the value of R1 here is almost the same using KVL. Same computation as the previous one, 10 volts and 500 ohms. Also though, current will not flow here because the switch is open. So current flows into the RC2 and to the LED. Using KVL, we know now the voltage drop because RC2 using KVL BCC RCBD 6 to the ground. Voltage drop at RC2 now is 10 volts. And using Ohm's law, since we know the required current 0.02, using Ohm's law here, we got 500 ohms, the value of RC2. So we computed the value of RC2 here, and RD1 here. Same computation as the previous one. Now, I said I choose the value of 590, arbitrary value, since we're going to connect like this one. To connect this output of the buffer to the input at this node should be matched 590. So let us now continue. That is the current flows when you close the switch at this state. transistor is open, conducting in cutoff mode. So the current will flow here. Since this is open, current will flow here. Also, the current will not flow here because the switch is open. No triggering base current, making this transistor to operate in cutoff mode. So let us now push the button. When you push the button, LED turns up. So when you push the button, switch on, push the button, LED turns off because the transistor now is operating in saturation mode, making this LED turn off. Upon pushing the button, we now calculate the values. We have a KBL here at the base and into the collector. Transistor in saturation. First KBL here at the base. Voltage drop R2, RB2, BE set. Then we have this equation. We can compute for IB, since this is dependent. The IB is dependent on the, based on this configuration of the transistor, is dependent on the transistor current gain, IB. We can compute the base current using the transistor formula HFE, IB, IC, IB. And also we know that the collector current now is the saturation current that flows into the collector, 0.02. And also we know that HFE, the same transistor, BC547, given datasheet, we get now 0.001 ampere base current that flows upon closing the switch. Now we have a series current, a series resistor with a base current of 0.001. We can now use this equation 1. Same, BR2 plus BRB is equal to 11.3. Using in terms of Ohm's law, we get now, since the base current is 0.1, they are in series. In terms of IR computation, we know the value of R2, 590. We get now, by computation, we get 112,410 ohms. So we know the value at the RC2, RB2, R2 is arbitrary values now for the values of the input LED. Upon closing the switch using KBL, we now got this value. 10 volts, also 10 volts, 500 ohms. Every time push the switch, current flows to the LED, lighting the LED, so that's why it is turning on. And the output LED is turned off because the current flows into the transistor. So every time push the switch 1, there's no output. And this is the logic symbol, 1, 0. So we now come here, the complete values. So get 5 load supply, 12 volt supply here. We get RD1, 500 ohms, R1, switch, LED grounded, transistor 1, RB1, 112,500, RC1, 590. And then the input of the buffer, we have provision here for connection of the input of the buffer at pin 8. Then the output LED, we're going to patch it by 5 and 6 pin. And then we have this power supply interconnected. For the inverter, we have this RD4, 500 ohms. We have the LED, the power on LED of inverter. We get this switch, we got this R2, 590 ohms for the impedance matching. When you're going to use this buffer to switch on the inverter, pushing the switch, making the current to close, patching the output into the input, making this 112,400 ohms in series with the 590. See, the current will close into to 590 and to the 112,410. So that's why we have this matching. If we're going to use the switch here for manual, we got this 590 in series with 112,410, which is also equal to as if we're going to use this whole circuit as in replacement with the switch here, because the output here going to the input just like this one. And that you seen here, I have the connection. We have the connection of the switch, patching the switch, and then for the input we have here 500 ohms for collector, and then the LED output of the inverter, and only one power supply. We have this vacant pin out. So if we're going to use the buffer, just patch the output to the input. This is the PCB layout of the buffer and an inverter. We have this PCB layout. As you've seen here, the buffer, the header. So that is the complete values, the calculation, and the operation of the circuit. We're going to use the buffer and the header, and the inverter to make an integrated circuit by patching it to the header. Okay, we have this calculation, PCB layout, circuit operation, and how to make the transistor circuit using transistor to make a buffer and an inverter logic gates, connecting the two. So we got this here, there's no output, no input, no output, with input in the inverter. With input at the buffer, output 1 becomes the input to the inverter, but 0 at the inverter. Okay, thank you for watching. Bye.